Hi students, I will share with you guys some of the thought processes required to solve structural elucidation question using some of the spectra given. Many a times the students will, your seniors often have difficulty trying to get the structures out. Okay, there is no one size fit all strategy, so all of us we need to find our own voice. So I hope that by sharing with you how I will do it on my own, it will be able to kickstart your thinking in how can you actually develop your own voice in solving questions like this. Okay, so we'll begin with question 2. Pretty fortunate for question 2 because you are given the molecular formula. Okay, so once you are given the molecular formula, actually things will be a lot easier because you can easily calculate the degree of unsaturation from here. So if you do a quick calculation, you should be able to get 5. Okay, 5 degree of unsaturation. You usually it tells you that it has a phenyl ring and maybe another either a ring or a double bond system. The reason is 5 degree of unsaturation. If you don't have a phenyl ring, there are just too many combinations and permutations, and it's going to make the whole elucidation process quite difficult. Okay, it's not that it's impossible to give you a series of rings and double bonds to test you on that. Okay, but any reasonable kind of test, you should expect anything 4 or beyond, right? You should have at least one phenyl ring. Okay, but you can easily verify this because if I just scroll down, you'll notice that you have 5 aromatic protons. Okay, so this basically tells you that you have a mono-substituted benzene ring. Okay, so that kind of like agrees with our initial postulate. So 4 degrees of unsaturation is due to the presence of a phenyl ring. Okay, then there's one more. So what can we tell from that one more? Okay, so if you just do a quick glance, if you wish, CC double bond usually don't show up very well, but of course you notice that I have a CO stretched, a strong CO stretch. Okay, very prominent signal. Okay, so in that case you can confidently attribute this to a carbonyls. Okay, so with this coming into the picture, then you can start working on the structure because you already know that there's a phenyl ring and there's a CO double bond. Okay, as to whether you should start with IR, mass spec, or NMR, it's entirely up to you. It's your own preference. Personally, if you ask me, I would prefer to perhaps do a quick glance at the IR to see the key function group. So in this case, we know that there's a CO double bond, and then there's a couple of interesting signals here. If you just cut at 3000, okay, slightly above, you would expect sp2ch stretch. Okay, not very strong signal, just shows a little bit, depends on how you run the spectrum. And then you realize that somewhere over here, it's our usual sp3ch stretch. Not very inspiring, but most of the combo has sp3ch anyway. Okay, but if you stare a little bit hard at this interesting peak slightly below 2900, you'll notice that these are pretty characteristic of a aldehydic CH stretch. Okay, how am I so sure that I have an aldehyde? Well, I can't be sure from here, obviously. I can just go on to the NMR. So based on the NMR, can you actually see that I have a signal close to about 9.6, 9.7? Yeah, so this is typical of aldehydic protons. And because it's being split into a doublet, so from here, if you kind of like want to derive the structure a little bit, you will probably be expecting an aldehyde group here. Okay, and then maybe I have H here that can potentially couple to the aldehydic H in order to give it the doublets. Okay, and then as to the rest of the structure, I'm not so sure, so I'll just move on for now. Okay, okay, so I'm done with IR. Then of course, the next thing is to actually look at the mass spec. The molecular ion peak is likely to be this, although it's not indicated. You can easily infer that it's 134. Okay, and the base peak. Okay, very nice base peak. Okay, so this one, if you do a quick count, 101, 102, 103, 104, 105, 105. Okay, so if this is 105, right, this is easily a M minus 29 peak. Okay, so what exactly is M minus 29? So 29, the thing that comes to your mind is likely to be an ethyl group. Okay, ethyl group. But if you scrutinize your particular structure here, right? Okay, let us just do a quick count lah. My final ring 6 carbon. Okay, and I know that I need to have these 2 carbon here. Okay, 6, 7, 8. Okay, then there must be a 9th carbon somewhere. So in that case, I can't have a ethyl group anywhere, because if I have an ethyl group, then I will exceed 9 carbons. Okay, so in that case, this 29 is not your usual ethyl group. If you stare a little bit hard at it, you probably will recognize that for aldehyde C, O, and H combined, right? They likely to give you a MR of 29. Okay, and in that case, that kind of makes sense, right? Because I have a base peak, so that means that this base peak is likely to be stabilized somewhat. If not, it wouldn't be so stable. And with this coming into the picture, maybe you can envision that probably my final ring must be therefore bonded directly to this benzylic carbon. Okay, because if you kind of like add them up, then that gives you 8 carbon, and then there's one more carbon should be bonded to here. Okay, are we able to tell that very quickly? Yes, because you notice that the most shielded carbon here contains 3 protons and is actually a doublet. Okay, very clearly shown here. Okay, so in that case, I can predict a CH3 here. Okay, and then does the rest make sense now? Let us do a final check. I have a pretty nice little quintet here, so if I do a quick count, I have 1 proton, 2, 3, 4, and therefore this H is likely to be split into a quintet. Okay, and having a chemical shift of about 3.8. Does it make sense? Again, yep. I mean, number one is it's due to a phenol ring. So phenol ring, if you look at the data booklets, chemical shift for the benzylic proton is about 2.5, and then it's next to the aldehyde group. So the alpha proton next to aldehyde group. Usually you expect chemical shift to be about 2.5 as well. So remember previously we were talking about the effect on the hydrogen, right, is not additive. Okay, you need to give it like maybe a 70% discount, 75% discount. Yep, so in this case you get about 3.8. So that kind of like make a little bit of sense here. Okay, so therefore in this case I will predict that my final structure is likely to have a phenol ring bonded to a carbon, benzylic carbon, and then H here, and then an aldehyde. Okay, and then CH3. Okay, so in this case I have a chiral center. Okay, then of course some of you might be wondering, hey, can I have a structure that looks maybe like this? Let's say you anyhow draw and then you get something like this. Okay, this is definitely unlikely, because in your 1H NMR the peak is not being reflected. Okay, because if I have a benzylic carbon here and I have an alpha carbon here that is next to the aldehyde group, I expect their chemical shift to be quite similar, maybe about 2.3 to 2.7. Okay, but this is not reflected in your 1H NMR, and at the same time I expect this to be a triplet. Okay, and this is not reflected as well in the 1H NMR. Okay, so maybe can I also bring to your attention that it will be good for you to kind of remember some splitting patterns. So this is a typical example of a ACH2 CH2B system. Okay, so in this case I'm afraid that the only answer that we will probably accept is the one that I've drawn here. Okay, I've circled in purple. Okay, maybe just a little bit of extension on this particular structure. The interesting thing here is that if you look at the actual 1H NMR, you're not going to actually get a quintet. Remember that earlier on we said that this is actually a quintet, but if you look at the actual NMR, if you do a little bit of expansion out, you realize that this looks like a weird looking quartet. Okay, but if you look at each individual peak of the quartet, it seems to be splitted into a doublet. So we call this doublet of quartet. Okay, so that means that the benzylic hydrogen, the extent of being splitted, right? It's different, okay, by the different hydrogen. And I think we can easily understand this. Okay, why is that the case? Okay, so let me just redraw the structures here to make it a bit easier. Okay, so if we were to look at our structure here, right? If I have a phenol ring, I have a H here. Let's call it HA. Okay, and then I have an aldehyde with a H. Maybe I call this HB. And then I have a methyl group. Let's call this HC. Okay, you realize that HB and HC are in very different chemical environments. Okay, so one is bonded to a highly electron withdrawing carbon on carbon. The other one is it's simply next to a sp3 hybridized carbon. So in that sense, right, you expect that when HA and HB, the proper term we're using here is when they couple to each other, the extent of coupling is different. So in this case, usually in NMR we represent coupling with the letter J, and if in this case this is the usual 3 bonds away coupling, we call it 3J coupling. So for the 3J coupling of A and B, right, you realize that the magnitude from the expansion below is actually quite small. So if you look out on the internet, it's around 2 Hertz. So coupling is in Hertz. Okay, then for the HC and the HA coupling, so this is all 3 bonds away, 3J and AC coupling. The magnitude is bigger, so this is 7 Hertz. Okay, so if you are, as I mentioned in the teaching solution, if you are interested in finding out a little bit more about coupling, you can just read a little bit more about it. No need to really go into the math or the complicated stuff, but appreciate the way the protons are being splitted. So in this case, if you look at HA alone, first it gets splitted like this, okay, into a quartet, and then within each of the quartets, it gets splitted into mini doublets like this. Okay, so that's why you end up with the peak with this kind of magnitude. Okay, can so I hope this little video gives you a little bit of a glimpse in how do we go about doing structure elucidation. Don't really need to follow like I must do NMR first, then IR or mass spec or whatsoever. Okay, so just follow your heart and find your own voice.